So in our last video, we talked about vector variables in ease and how to use them. So how to assign them, and then also how to carry out simple vector operations like addition and subtraction. In this video, we're going to discuss how to take the dot and the cross product of two vectors. So the dot product of two vectors is a scalar, and the scalar is given by this equation here. So A dot B is just the product of the magnitude of A multiplied by the magnitude of B multiplied by the cosine of the angle between them. And in Cartesian coordinates, you would calculate a dot product using this equation. So you would take the x components of the two vectors, multiply them together, and add them to the y components multiplied together, and then finally add them to the z components multiplied together. In ease, you can use the vector dot function to calculate a dot product of two ease vector variables. So the vector dot function will take as its arguments two vectors. So here, as an example, I will just define two vectors A and B using the vector assign function. And then I'll use the vector dot function to take their dot products. So that's what A dot B here is. And then I'll just do it also manually to show that if I did it right, I should get the same answer. So the dot product is used for a lot of things, but one thing it's used for is to decompose, for example, a force F into components F parallel and F perpendicular that are parallel to and perpendicular to some direction defined by a position vector R. And that's what's shown in this figure. So the magnitude of the component parallel to the position vector is just the dot product of the force with a unit vector that is in the direction defined by the position vector. So that's this equation. And if you want the vector component parallel to the position vector, you would just multiply this magnitude by that unit vector. So that's F with an arrow. The vector component perpendicular to the position vector you can get from this vector equation, right, which just says that the force perpendicular plus the force parallel has to be equal to the force. And the magnitude of the component perpendicular to the position vector is given by this equation, which makes sense given that the parallel and the perpendicular components are two sides of a right triangle here. The cross product between two vectors is another useful vector operation. And in general, the cross product of two vectors is itself another vector, and it's defined according to this equation. So the cross product of A and B would be the magnitude of A times the magnitude of B times the sine of the angle between them. And then this U, this is the unit vector that is normal to the plane containing the two vectors A and B. And it's going to have the direction defined by the right-hand rule. So that's what's shown here. In Cartesian coordinates, the cross product is obtained according to this equation. So A cross B has three components, I, J, and K, and you get them according to these equations here. The cross product of two 3D vectors in ease can be obtained using the vector cross function. And the vector cross function takes as its arguments two vector variables. So here I've just defined a vector variable A and B, and A cross B is itself a vector, and it is obtained with the vector cross function A comma B. And I can do the same calculation here manually, where I'm just calculating the x, the y, and the z component of another vector. And if I did that correctly, you can see that I get the same answer either way. Note that the product of two 2D vectors will always be a vector in the z direction, right? So if your 2D vectors lie in the xy plane, which is how 2D vectors are defined in ease, then the cross product will be a vector that is in the z direction. You often want to take the cross product of 2D vectors when you're computing a moment, but in this kind of calculation, the result can be interpreted as a scalar, and therefore the function vector cross, when you apply it to two 2D vectors, will return a scalar. And the scalar is just the magnitude of that vector in the z direction. So you can see here, I'm taking the cross product of 2D vectors A and B, and the result of that is just a scalar A cross B. So in the next couple of videos, we will go through examples that require first the use of the dot product, and then the use of the cross product.